θα υπάρχει, αλλά εγώ χρησιμοποιώ Keynote. Έχει κάποιες συντομεύσεις, αλλά ορίστε.
Ωραία, τέλεια. Οπότε να ξεκινήσουμε, αν είμαστε έτοιμοι όλοι. Κύριε Βέπα, κύριε Κουτρούλη, να ξεκινήσουμε. Ωραία. Τέλεια.
Λοιπόν,
Οπότε ξεκινάμε με την εξέταση και παρουσίαση της διπλωματικής εργασίας του κυρίου Σαούλη Λάμπρου, η οποία έχει τον τίτλο που βλέπετε στην οθόνη, Διαστασιολόγιση συστήματος τροφοδοσίας με ηλεκτρική ενέργεια για τροφόσιτο με φωτοβολταϊκά και εναλλακτήρα. Λάμπρο, έχεις 20-25 λεπτά για την παρουσίαση και μετά θα ακολουθήσουν ερωτήσεις, εντάξει?
ωραία, θα κάνω το κατά δύναμη να προλάβω αυτό το χρονικό όριο. Έγινε. Okay, so I'll do it in English. Hi to the examination committee. I'm Labros, and I'm here to present my thesis on the dimensioning of electrical power supply system for motorhome with alternator and photovoltaics. So the outline of this presentation is divided into 6 sections, which include introduction, number 2, literature review, dimensioning, modeling, simulation, and conclusions. Now on to the introduction. Initial idea started in 2016 when architect Platon Yannakakis from Technical University of Crete had the need to make a motorhome for recreational events. The implementation of the electrical department was partially undertaken in the study for the thesis designing a vehicle conversion into a self-propelled residential co-creation and events unit. Personally, relating to this project, I've been motivated finding a solution to counter-battle the lack of street-level expression, drastically starting from the epidemic of COVID-19. Other factors that have contributed to this diminishing human aspect, such as credit current usage affecting economically and socioeconomically, and the broad use of smartphones, to name a few key points. The scope of this thesis is the mobile electrical power autonomy for civil recreational needs. So a few words of the components being used in the power system. Photovoltaics, also known as solar or photovoltaic panels, all consist of solar cells. Photovoltaics over the years have been developed based on user needs and can be categorized into 2 types based on their usage, residential and commercial. Here you can see some distinct physical characteristics of both. There are 3 main types of solar panels: monocrystalline, polycrystalline, and thin film, each categorized with common attributes. The characteristic curve of solar panels show all the possible combinations of current and voltage for energy production. The temperature exposure also affects the power production, thus the graph. Here are some common picked off a variety of data sheets. So alternators now are mechanical devices that convert circular motion to electricity. In automobiles, they are placed near engines, crankshaft connected via drive belt. The parts that come in contact with the drive belt to spin is called the pulley. The relation between the rounds per minute of 2 pulleys is the ratio of the greater one divided by the smaller. This is called the pulley ratio. The parts that produce energy is movable rotor and the stationary stator. Through the voltage regulator, the voltage remains constant, and through the rectifier, the ampere output is converted from alternating current to direct current. The higher the RPM, the more energy is produced, and taking into account the temperature, the lower the temperature of the alternator, the more energy is produced as well. Now, batteries contain chemicals, and energy is created and stored through their reactions. There are 2 types of batteries, which are the primary, used only once, and the secondary, which are used multiple times because they can recharge. Batteries are laid out in cells which consist of a module, and many modules create a pack. The basic structure of a battery consists of a positive and negative terminal dipped into an electrolyte. Both terminals can also be named cathode and anode respectively. When a battery is charged, current flows from the positive to the negative terminal and the opposite when discharging. Below we have the chemical reactions of a lead acid battery, as we can see here, where a little bit of chemistry is involved there. So, the main types of batteries are lead acid, nickel cadmium, nickel iron, nickel metal hydride, and lithium ion, with lead acid batteries having the most subcategories shown in the graph. Basic conditional parameters are the state of charge, the depth of discharge, and the battery and the capacity of battery, which varies depending on the discharge rate. The lower the discharge rate, the more adequately acid can be supplied to the plates during discharge reaction depending on the depth of discharge. So other parameters include temperature and the number of cycles out of its lifetime. Okay, cursor. And there are more technical specifications here. So now onto the power converters, which are devices that convert a power system's input amperage or voltage to a desired output level via switching techniques. They consist of inductors, diodes, switches, and capacitors. There are two types of converters: direct current to direct current converters, which subdivide in buck converter that reduces the voltage, boost converter that increases the voltage, and buck boost that could do either or. Now, the other type is direct current to alternating current converters, are also known as inverters, and there are two types: single phase and three phase. Single phase inverters are designed in half bridge and full bridge, with that last activating a pair of switches. At higher power levels, a three-phase inverter is used. The three pairs of switches are switched in a cyclic manner with a 120-degree phase shift. Now, these are some other common specifications. I'll not go into them, but you can see them here. The total harmonic distortion is very important because there's a sine wave quality evaluation, and because the implementation is based on, also uses sound amplifying devices that could affect the sound quality of the speakers. So cables connect all the components together, and it's how the power system transfers energy between components. All cables consist of the conductor and the insulator. The conductor can be made out of aluminum or copper, copper being more expensive than aluminum, losing only at the attribute of expansion and electrical conductivity. The conductor comes in forms of a solid wire or stranded. The skin effect is an important factor to take in consideration when choosing solid or stranded conductor. When alternating current goes through the conductor, current density gathers around the skin of the conductor, resulting in higher resistance. Stranded wire is affected more by this effect due to more skins. Now, insulation can be made out of plastic, rubber, or the fire resistive material fluoropolymer. The outer part of the insulation can be labeled with different initials, and the color can mean either ground, positive, negative, terminal, depending on the standard use. Now, the load is considered anything that consumes energy, and there are three types of load: resistive, inductive, capacitive, which differentiate all based on the relative phase of the current and voltage. In a resistive load, current and voltage are coherent. Inductive load, the current and voltage are incoherent. The current precedes the voltage. And the opposite happens in capacitive load, which cannot exist in a standalone format. Now, to the dimensioning of the system, we got photovoltaics are placed on a 9 square meter roof, and a maximum of 4 panels can fit, except if an extension is created over the roof. The solar panel chosen is the maximum 450 watts by the company SunPower. Assumptions are made, so the solar panels are placed at a 0-degree slope to avoid aerodynamic drag. Azimuth is 0 degrees, meaning vehicle is always parked facing north, and the vehicle is parked in an open area to avoid shade from the surroundings. The circuit configuration is in series given the electrical and physical characteristics here, as we can see in the table. Now, an additional alternator is installed on a mount requiring a longer drive belt and is installed near the engine. The rule of thumb is the size of the alternator must be 20 to 25% of the battery capacity. The current produced cannot exceed the charging current the battery can handle. In this case, having two power sources, the sum of both alternator and solar panel energy production is the limit. Alternator chosen is 28 volts, 140 amperage, and the model is from model AAT by Czech company, as you see. There are two loads in the power system, one for household use and the other is for recreational use. The household is based on the user's daily routine, and the time activation of each appliance can be estimated, and the overall load is calculated. Now, the special events load, L2, is based upon a standard live rock/EDM music setup. All sound amplification devices run no more than 1/8 of the nominal power consumption, although can differ based on the genre of the music. For safety reasons, a quarter of the power consumption is considered, as we see here in the formula. To sum up, 7,830 watts, rounding up to 9,000 watts, considering a 15% safety margin for load 1, and 6,200 for load 2, considering that the live will run for 3 hours. And that makes it to approximately 2,100 watts watt hours per hour for the live music setup. So times 3, that makes it to the number you see at last. There is one inverter for the electrical power system, and the two main parameters to consider is the continuous power and the surge power. Other factors that are important is the pure sine wave, the reasons that we said before, and low total harmonic distortion, which basically, yes, okay, continuing on. To size the energy of the inverter, the maximum continuous load is calculated in the case all loads are turned on at once. After that, we have to seek that the devices being used have a motor or compressor, such as an air conditioner or a refrigerator, and calculate the surge power, which is usually 1.5 to 2 times the continuous power. Then the apparent power, can be calculated multiplying the continuous power and the power factor, which is commonly 0.8. So, to sum up, the household load needs an inverter of 10,080 watt hours, and the special events loads requires a 2,080 watt hours. So we choose the second one, the largest one, which is chosen as an indicator for a suitable inverter. Now, 2 batteries, B1 and B2, are used in the study satisfying each load, L1 and L2 respectively. This formula calculates the capacity calculated for each battery. So we have a rounded 440 ampere hour for battery 1 and a 320 ampere hour for battery 2. That equals 2 batteries for the household load connected in parallel and 1 for the special events using the lithium battery from Renogy, as we see here in the figure. Here we see the dimensions of all batteries and the series connection of battery 1 and battery 2 is solo. The battery selected here in type lithium due to its high power density and relative power to weight ratio. Now on to the modeling of the power system. So here we have the power system energy flow diagram emphasizing the connection to the DC and AC buses. Solar panels and alternator connected in parallel to a standard solar charge controller and then connected to the DC bus. The alternator is driven by the diesel engine. The DC bus outputs energy to the battery banks and the inverter, so the inverter can be drawn from the 3 power sources at any time, and the AC bus delivers to the loads. Here we have a more detailed depiction of the power system. Energy enters the system from the sun and the burning of fossil fuel and is transferred to the charge controller to both batteries. The loads are connected to a 230 volt alternating current bus, which is connected to a relay switch controlled by the charge controller. The component of automobile which contributes to the motion of the vehicle is called the powertrain, and the parts examined are engine, transmission, and rear axle. The wheel also plays a role in calculations, but not analyzed here in depth. So the car engine used is called the SOFIM 8140.43. The submodel used is the S, chosen because of its wider range of values in power and brake-specific fuel consumption. The gap between 800 to 1200 RPM is covered using the interpolation method, and all the information is then structured in a lookup table. The transmission used in this simulation is a 6-speed synchronous named 2840.60D. The gear shifts based on the fixed vehicle and imposed engine speed, meaning that the shifting occurs after a threshold set based on the maximum RPM the engine can reach. Here we have the gear ratios depending on each gear and the top velocity calculated in each gear, creating speed and gear corresponding intervals. Photovoltaic energy production is based on this formula, and the graph of the ampere output of the alternator is stored in a lookup table. Here we see a simulation and the ratio of RPM of the alternator and the engine crankshaft. Now the battery is modeled as a bank of energy measured in kilowatt hours with no additional parameter of loss, meaning the draw of energy is a subtraction of the energy reservoir and the load demand. Excess energy is saved to the batteries, adding to the reservoir. Now, the charge controller operates with a clear priority, always ensuring that the household L1 is satisfied and battery B1 is charged before battery B2 for the live venue. The charge controller operates with a clear priority, always ensuring that the household load L1 battery B1 is charged before the live venue of the battery. I'm repeating myself and I excuse myself. This system is made possible by the charge controller's inbuilt programmable microcontroller and relay switch, which monitors the state of charge of B1 and channels the power source switch to B2 only when B1 is fully charged. When the user takes the initiative to switch the relay manually on, the channel opens to battery 2 for discharging also. After B2 discharges at the predefined depth of discharge, the channel closes to its first state with ability to charge and discharge B1. Prioritizing this way, as I said before 3 times now, prioritizing the household use channel. So here's a physical implementation with a charge controller and the relay switch, which is manually turned on and turned off electronically. So taking my cursor here, I see. So if B1 is not fully charged, then continue charging or else charge B2. If B2 predefined depth of discharge, then send control signal to turn off switch. If control signal is given and switch is on, then turn off. Here we have an abstract model of the system's input and output. The input is the solar radiance and the load. Output is the consumption curve, cost functions, and kilowatt hour production. Here we have the solar radiance taken from the National Renewable Energy Laboratory located here in the United States, and load here in particular, as we see, is the worldwide harmonized light vehicle test procedure, which is the WLTP, also abbreviated, which is a global standard for measuring a vehicle's fuel efficiency, emissions, and range. Now, the output is a formula used to convert the brake-specific fuel consumption graph to liter per hour. And here we have different economic values such as cost of operation, cost of energy, and solar power production. So on to the simulation now, which is subdivided into evaluation, scenarios, and the results. So the simulation tool, so data was acquired and processed through several programs. And the first in line is the web plot digitizer, where all the data sheets graphs are inserted into the program, which recognizes the graph and samples it at a chosen rate by the user. The other program used is MATLAB, where here we see a series of algorithms process that data from the engine and the alternator and compute the desired outputs. The first stage is to import data in the forms of a CSV files, and the alternator, engine, and vehicle in general. Those are okay. Excuse me. Then the data is processed through conversions, formulas, and sum-ups. Last, the data is exported into desired outputs. So here we have the algorithms. I won't go into depth of that. They're relatively simple. So all the information retrieved is inserted into a Microsoft Excel, where every component and condition of the solar system is in separate worksheet tabs. They are 7 identical and interconnected consecutively spreadsheets that represent an hourly sampled day, and divided into input power sources, output power, energy compensation, energy storage system, and expenses. As you can see up high on the file, titled. So in each cell, conditional parameters are set to simulate the bounded battery capacity, setting higher and lower limits, the finite state machine implementing the charge of the battery priorities mentioned earlier, and alternator production depending on which speed range it belongs to. So this is the graphical output. So we have the state of charge of battery 1, the hourly load, the sun irradiance, and the power production from the alternator. So here we are onto the evaluation. We have taken different cases here to evaluate the performance of the alternator, the engine, and the alternator engine. Okay. So here are the results. I'll just move on for now. So this is the scenario design. We have taken 3 scenarios, and also must mention that I'm going into depth. So seasonal, we have 3 scenarios: seasonal, cloud effect, and graphical effect. So the seasonal effect, the energy production in number 1 is reduced by 24%, with summer having the highest yield of energy. And this is how it's divided. So based on a trial error, the following measurements have been taken. We have the cloud effect. So a little some words for that is. So I'll go on and say the autonomy is examined solely on solar power, and then the use of the alternator engine to compensate the unsatisfied hours. In wintertime, when the weather is coldest, the energy autonomy lasts up to a day. To maintain it, the user must travel every other day to recharge the household. In the fall, the autonomy lasts for 2 days, and in the case of cloudy weather, the autonomy is reduced to 1.3 days, which is a 35% reduction of autonomy. In spring, the average autonomy time is 5 days. If all 7 days are cloudy, the power system autonomy is reduced by 2 days, which is a 40% reduction. In the summer, the power system is completely autonomous, even when there are clouds all week. So there's a scenario examining the cloud effect. So that was just the seasonal effect examined. Now the scenario examining the cloud effect, this has been examined in 2 ways: the number of cloud days of the week, observing a 3 to 4% reduction in energy production. And now another factor examined is the day of the cloud day occurrence. The day that the clouds occur affect the number of overload hours, which are basically the unsatisfied hours. The behavior of the power is simulated in clear and cloudy sky for 7 days. Then the simulation takes place at a 1 to 7 days of continuous cloudiness at the beginning of the week, and then the next day of series of cloudy days, making up to a total of 29 cases, as you can see. So the grays are the clouds, and the whites are the sunny days, as you can see in the graph. So this is the full scenario based on the initial idea of mobile energy autonomy for living and co-creating. In particular, testing the system's power autonomy under a scenario of an American tour divided into 3 trips based on the grouped sun irradiance levels. Driving in between stops is divided by around 4 hours, so from one stop to another. There are 4 hours of continuous drive, taking in consideration the global legal law limits. So starting from Mexico, going all the way up to the west, all the way up to Washington, yes, Oregon, excuse me. So here we have the results. We have the genset hours used in order to satisfy the load, the drive hours, the total of each week. So it starts, let's go down below number 1. So from number 1 point to number 2, the drive hours are, so yeah, there's a balance between genset hours and drive hours. So drive hours are more preferable because you could drive and do some jobs around the particular area where the car has parked. So this is a balance of a person turning on the engine to satisfy his load. I'll just move on, and so yeah, this is a total of 10 weeks. So in each stop, he stays there for a week and just tries to satisfy the load either by driving or leaving the car on idling. Here we have the East Coast tour. So it's a basic continuum from the first one, as you can see. So the number 10 is number 1 on the East Coast. So this is the route of the East Coast. And then we go on to the Canada tour, which degrees are much more lower. So the results are, every week the car is parked. Yes, here I say it. Excuse me. Okay. Every week the car is parked in order to maintain the power system energy autonomy for the household load L1. The sun irradiance is not enough for the solar system to satisfy all loads. To cover the energy depth, the user has to either turn on the engine idling or travel with the last being preferable. The East and West Coast trip have very similar results. As for the effort put in for energy autonomy compensation and defer only 0.1 hours. The Canadian tour has the biggest difference compared to the other tours, excuse me for mixing up the words, of 1.7 to 1.8 in genset hours and 5.1 to 5.2 in drive hours. And here are the conclusions to finish this off. By examining the power system, putting it to the test, and analyzing the results, conclusions can be drawn for the power economic economy. All the values are mathematically proportional to the speed of the engine, the vehicle, which determines the gear clutch, and therefore the engine RPM of the alternator, RPM ratio, and the energy production. There is no constant round up the energy production of the alternator. Every velocity, excuse me, one moment. I'll take my cursor and put so I can see. Yes, thank you. So going again, there is no constant roundup energy production of the alternator. Every velocity the automobile reach has a significant impact on the energy production. The alternator charges approximately twice the energy when the car is moving than when idling. A 20% reduction in solar irradiance due to clouds decrease energy autonomy by approximately 40%. The cloudy days of the week do affect the number of overload. The first and second days of occurrence are cloudy. Happening later in the day will reduce the number of overloads. The increase in photovoltaic efficiency does not greatly impact the overload hours. There is no significant difference between the East and West Coast tour. Sampling further geographical above, where temperatures are lower, shows a 33% decrease in total average drive engine alternator time and therefore overall cost. The colder the weather, the more the user has to travel to maintain energy autonomy, and the higher the cost of operation. So the proposed system is self-reliable for household use. However, the event load system must be charged from an external source. And the future work that can be done: the addition of a wind turbine is a practical solution to increase energy production, thus making the power system more reliable. Taking more samples so there could be a better understanding of the power system. Considering more parameters such as temperature, road incline, and engine torque. Heat loss from cables could increase the number of conclusions, although some might have an imperceptible effect on the power system of the study. Take into account the torque of the engine, the same as the other bullet, which is a dash I said before, basically. So on to the next one. The effect of adding an additional alternator and the contribution to the fuel consumption. Calculation of the capital cost of solar power system and estimate the payback period and the cost of energy, COE, of solar power. Now, discussions, since cost is not a limitation, it is worth investing in a higher output alternator that will pay off in the long run. This would be ideal for year-round use to satisfy the household load life system use. Yes. I made it in 31 minutes. 31 λεπτά.
Λαμπρό, θα περάσουμε στο κομμάτι των ερωτήσεων. Θα ξεκινήσουμε τον κύριο Κουτρούλη.
Καλησπέρα. 2 παρατηρήσεις έχω σύντομες γιατί δεν έχουμε πολύ χρόνο. Το πρώτο είναι στο κείμενο, στο εξώφυλλο. Θα πρέπει να αλλάξεις αυτό που γράφεις New York 2024. Στα Χανιά είμαστε. Πολυτεχνείο Κρήτης στα Χανιά.
Πράγματι.
Εντάξει, ναι. Πριν το παραδώσεις δηλαδή στην βιβλιοθήκη.
Α, ναι, σωστά. Α, νόμιζα της παρουσίας. Α, όχι, εντάξει.
Όχι, στο κείμενο της διπλωματικής.
Οκ, εντάξει.
Εντάξει.
Κάτσε να το σημειώσει, γιατί αυτό το ξεχάσω.
Η άλλη παρατήρηση, η άλλη ερώτηση μάλλον, διευκρίνηση. Με ποιο κριτήριο έχεις επιλέξει τα φωτοβολταϊκά, τα συγκεκριμένα που είπες?
Από μια έρευνα ήταν τα πιο αποδοτικά που βρήκα. Ναι, τώρα να σας πω την αλήθεια, τα έχω βρει καιρό τώρα. Τώρα δεν ξέρω αν έχει εξελιχθεί τόσο η τεχνολογία ώστε να υπάρχουν πιο...
Κριτήριο, θέλω να πω.
Το κριτήριο ήταν το maximum watt hours. Τα maximum watts. So ήταν το πιο από τα... Ναι, το maximum wattage output of the solar panels I could find.
Και η επιφάνεια δεν έπαιξε ρόλο σχέση με την επιφάνεια που θα μπουν?
Yes, because it's standardized. Όπως ανέφερα, όλα τα φωτοβολταϊκά είναι πάνω κάτω, αν όχι όλα δηλαδή, είναι το ίδιο μέγεθος. Δηλαδή, όλα τα φωτοβολταϊκά στην αγορά είναι πάνω κάτω ίδιες διαστάσεις. Όχι πάνω κάτω, τα περισσότερα εμπορικά που θα βρείτε. Οπότε καταλήγουν να μπορούν να χωράνε 4 στη συγκεκριμένη επιφάνεια, εκτός άμα, όπως ανέφερα, κάνεις ένα extension να χωρέσουν 5. Στη μελέτη που έκανα είναι 4.
Εντάξει, ευχαριστώ. Δεν έχω κάποια άλλη ερώτηση.
Οκ, ευχαριστώ.
Ο κύριος Πέπας.
Λάμπρο, πολύ καλή δουλειά.
Ευχαριστώ.
Στη δημοτική σου. Σε συνέχεια αυτό που ανέφερε ο κύριος Κουτρούλης, ήθελα να σου πω ότι υπάρχουν πολλές παράμετροι φωτοβολταϊκά, μεταξύ αυτών ο στελτής απόδοσης. Επίσης τα καινούργια που υπάρχουν είναι bidirectional, δηλαδή μπορείς και τις δύο μεριές να έχεις cells, άρα να αυξήσεις την απόδοση περίπου 20-25%, άρα έχει αξία να διαλέξεις κανείς φωτοβολταϊκά, όπως ακόμα μπορεί να βάλεις και υπάρχουν και αυτοκόλλητα, περιμετρικά δηλαδή του αυτοκινήτου που θα μπορούσε να βάλεις, όχι μόνο στην οροφή, με πολύ μικρότερη απόδοση φυσικά και ισχύ, αλλά είναι και αυτά συμπληρωματικά θα βοηθούσαν. Δεύτερο που θέλω να σου πω, αν έχεις λάβει υπόψη σου το κομμάτι της ηλεκτρικής προστασίας, γιατί προσαρμόζοντας κάποια φωτοβολταϊκά πάνω στη στέγη σου, τα οποία είναι αγώγημα και είναι συνδεμένα με το ηλεκτρικό δίκτυο, αν ποτέ έπεθε ένας χειραγνός που στην Αμερική είναι και σύνηθες, θα συνέβαινε σε αυτό το αυτοκίνητο. Γιατί έχει και μπαταρίες λιθίου, οι οποίες είναι επίσης εξαιρετικά επικίνδυνες χειραγνικά. Δεν ξέρω αν το έχει σκεφτεί ποτέ αυτό.
Όχι, δεν το έχω σκεφτεί. Οπότε προτείνετε μια κεραία αντικεραυνική ή έχετε κάτι στο νου σας για την προστασία?
Από το Ιώτα που έχει κάνει ένα αντίστοιχο σενάριο με φωτοβολταϊκά στο roof, συνήθως τοποθετείται ένα πλέγμα περιμετρικά σαν ας πούμε ένα μες από πάνω από τα φωτοβολταϊκά, έτσι ώστε να θα πέσει κεραυνικό, γιατί στην Αμερική έχουν τύχει αρκετά περιστατικά αυτοκίνητο να πληγεί. Και δεν είναι το θέμα σου, εσύ θα πάθεις κάτι γιατί είσαι εσωτερικά το αυτοκίνητο, αλλά τα φωτοβολταϊκά σου, τα οποία είναι διασυνδεμένα με την μπαταρία και τον inverter, προφανώς αυτά μπορούν να έχεις ζημιές, το οποίο είναι το λιγότερο, αλλά μπορεί να έχει και φωτιά στην μπαταρία σου. Οι μπαταρίες είναι αρκετά ευαίσθητες λιθίου σε κεραυνικά πλήγματα. Αυτό μόνο, αν θα ήθελες κάποια στιγμή να ασχοληθείς. Και το τρίτο που θα μπορούσες να κάνεις, να προσθέσεις και αναγέννηση κατά την πέδηση, έτσι ώστε να αξιοποιείς ένα έξτρα κομμάτι ενέργειας για να φορτίσεις την μπαταρία σου από την πέδηση. Έτσι. Αυτό. Κατάλαβα, πολύ καλή δουλειά και πάρα πολύ καλή παρουσίαση.
Ευχαριστώ.
Καλά.
Ωραία. Λάμπρο, εγώ έχω μόνο κάποιες λίγες διευκρινιστικές ερωτήσεις. Καταρχάς, είχες βάλει 2 όρια στο σύστημά σου. Το ένα ήταν το 9 κιλοβατόρες τη μέρα. Αν κατάλαβα καλά, έχεις σχεδιάσει το σύστημά σου με βάση ένα μέγιστο όριο καταναλυσσόμενης ισχύως ανά μέρα και ταυτόχρονα έχεις και κριτήριο ανά ώρα που είναι διαφορετικό.
Όχι, είναι κάθε μέρα, όχι, κάθε μέρα ο χρήστης κάνει μία στάνταρ ρουτίνα. Για παράδειγμα, η αλήθεια είναι, έχω και ένα γράφημα, αλλά τώρα καλύτερα να μην πειράξω κάτι άλλο από εδώ. Αλλά έχω ένα γράφημα το οποίο είναι στάνταρ, δηλαδή από το πρωί μέχρι που να ξυπνήσει, είναι αυτά τα φορτία. Όταν ξυπνάει, ξέρω εγώ, ανοίγει φώτα, κάνει ό,τι κάνει, μετά μαγειρεύει. Ξέρεις, υπάρχει ένα στάνταρ πρόγραμμα και με βάση αυτό υπολογίζεται το daily consumption of energy. Οπότε...
Αλλά είχες και ένα 6200 που ήταν την ώρα.
Όχι, αυτό είναι για το άλλο φορτίο των ζωντανών μουσικών events, των ζωντανών events. Αυτό υπολογίζεται είναι στα 1200, 2100.
Άρα αυτά τα δύο πάνε αθροιστικά.
Όχι, είναι ένα το ένα, ένα το άλλο. Ναι, είδες, είχα κι άλλο ένα γράφημα που είναι ουσιαστικά μπαταρία 1 με φορτίο 1, L1, B1, and L2, yes, B2, load 2 for B2. So το κάθε ένα είναι ξέχωρο.
Άρα αυτά τα δύο έχουν διαφορετικά όρια και είναι και ξεχωριστά μεταξύ τους. Γιατί όταν το πρωτοέδειξες δεν το κατάλαβα. Είχα την αίσθηση ότι είχες βάλει σαν μέγιστα κριτήρια στο ίδιο το σύστημα κατανάλωση ημερήσια μέχρι τόσο, αλλά ταυτόχρονα και ότι κάθε ώρα δεν μπορείς να ξεπεράσεις ένα συγκεκριμένο όριο για τη διαστασιολόγηση του ρεύματος που έχεις μέσα. Οκ, εντάξει. Το άλλο που ήθελα να μου εξηγήσεις τελευταίο είναι πες για ένα gap που πας να γεφυρώσεις μεταξύ 800 και 1200 RPM. Μπορείς να μας πεις λίγο, γιατί το πέρασες λίγο γρήγορα και δεν το κατάλαβα.
Ναι, είναι ουσιαστικά, άμα δούμε εδώ στο γράφημα της μηχανής, δεν αναφέρει κάπου, εδώ στα 800 με 1200 δεν έχει γραμμή. Οπότε αυτό το κενό έχει βρεθεί με βάση τη μαθηματικοποίηση των interpolation method, άμα το λέω καλά. Δηλαδή το interpolation method χρησιμοποιείται για να προβλέψει τιμές ενός γραφήματος τις οποίες μπορούν να λείπουν, ας πούμε. Οπότε με βάση αυτή τη μέθοδο...
Έχεις βάλει το full extent του profile του power. Τώρα το κατάλαβα. Το πέρασε λίγο γρήγορα και μπερδεύτηκα. Άρα τι, για κάθε σενάριο έχεις βγάλει τη συνάρτηση και μετά κάνεις απλά extrapolation πάνω στη συνάρτηση.
Ναι, ακριβώς.
Και τα profiles που ξεδώνουν διαφορετικά μεταξύ τους. Εξακολουθούν διαφορετικό.
Είναι... Ναι, συγγνώμη, δεν το κατάλαβα αυτό. Ότι τα profiles...
Για το κάθε μέγεθος, γιατί εδώ βλέπω έχεις το power, έχεις το torque.
Ναι, έχω ουσιαστικά πάρει in consideration το power και το πάνω γράφημα και το κάτω γράφημα. Το power και το brake specific fuel consumption, που μέσω αυτών των δύο τιμών και με βάση το fuel density, το οποίο το έχω μετατρέψει, το fuel density το έχει πάρει και αυτό σαν παράγοντας, για να μπορώ να υπολογίσω τα liters per hours για να παράξουμε το γράφημα που είναι το γράφημα του fuel, εδώ, το consumption curve. So, το πρώτο, the grams per kilowatt hours is the BSFC graph times the engine production, the power from the engine, στα συγκεκριμένα RPM, επί το λίτρο ανά gram, που είναι το ανάποδο του diesel density, και άμα κάνουμε αυτή την πράξη, βγάζουμε τα λίτρα ανά ώρα. So, εκεί χρησιμεύουν...
Ωραία, κατανοητό. Θα ζητήσω από όσους δεν είναι εκτός της εξέτασης, παρακαλώ να αποχωρήσουν. Λαμπρό, θα σε βάλω για λίγο σε ένα waiting room για να συνεδριάσουμε με την Επιτροπή και θα σε ξανακαλέσω μέσα για να σου πούμε την απόφαση, εντάξει?
Εντάξει.
Λάμπρο, με ακούς?
Ναι, σας ακούω κύριε Κώστα.
Κάνει unmute.
Ένα λεπτάκι.
Δεν σε ακούμε, κάνει unmute.